All right. How's everything going? Any questions before we get started on matrices and induction? PA1 good? Yes. Okay.
So on paper homework 7.2 number 8 A.
Can you tell me what it says? Oh. Well, let's pull it up here. So which chapter are we in? 7?
Yeah, 7.
And which section? All right, 7.2, which number?
8.
Number 8, define functions if they exist on the positive integers with the same properties as in exercise 7. Yeah, this is a fun one. So, part A is 1-to-1 and onto. Part B is neither 1-to-1 nor onto. Part C is 1-to-1, not onto. And D is not 1-to-1. So all possibilities. And you want functions on the positive integers. So do you understand what the question's asking? Okay, so let's look at that. Let's make a set S containing 3 elements. And let's make a set T also containing 3 elements. And let's have some function f from S to T. So question 1 is saying, can you define, this is a different question now, we're working with these sets instead of positives. Could we define a function from S to T which is both 1-to-1 and onto, injective and surjective, so bijective? So what does it mean to say that f is injective, 1-to-1? Maps to 1. So different things in S have to map to different things in T. Onto says that everything in T gets mapped to. So for example, f of A equals 1, f of B equals 2, f of C equals 3. That's both injective and surjective, right? So that's 1-to-1 and onto. So that would be an example there. Could you have a function that is neither 1-to-1 nor onto? So when does a function fail to be surjective? That's injective. Okay, so when does it fail to be injective? You have 2 things mapping to the same element. So suppose we said f of A equals 1 and f of B also equals 1. Right there, it's not injective anymore. And it turns out, whatever we map C to, whether it's 2 or 3, we're still going to be missing one of these elements in T. So this is not surjective either, right? So can we make something that's 1-to-1 but not onto? Well, it turns out in this case we can't. But suppose we set T equal to, so let's set W equal 1, 2, 3, 4. And let's have F go from S to W. Okay, that's still injective, right? Because different elements of S go to different elements of W. But it's not surjective because nothing's mapping to 3. And our fourth example, we want it to be surjective but not 1-to-1. Well, let's make a new set V, which contains the elements 1, 2, and define F from S to V. Bless you. So f of A could be 1, f of B could be 2, and f of C could be 1. And it's clearly surjective because every element in V is mapped to, but it's not injective because A and C both map to same. So there's an example of each. So question 8 is asking you to do the same thing, but looking at the set of positive integers instead of these particular sets, and see if you can find examples of these. Yeah. Let's see what it says. Define functions if they exist. So how do you define a function? Well, you can do it with an equation, f of x equals x squared. You can do it with something like what we wrote here, right? F of this equals that, f of this equals that. You could do it with a carefully written description, as long as it's pretty precise, but nothing too hand-wavy. You could do it probably with computer code. You could say something like, let f be the function that maps even numbers to 0 and odd numbers to 1. That's precise, right? But don't say, f is some function that takes most things to 0 but leaves a few others, blah, blah. Yeah?
7.3, number 2, but this one I have a question.
Okay. Well, I may as well scroll down there. So 7.3, number 2.
Oh, I mean, f of inverse 4, f inverse 4.
Ah.
The last
So do you remember what inverse functions are? So it looks like 1 over, but it's actually not. So for functions, so there's 2 arbitrary sets. And suppose f goes from T to S. So it's mapping from this set to this set. And our mapping is defined as follows. I'm just going to do 3 elements. So f of 5 gives you A, f of 4 gives you W, f of 10 gives you T. Okay, f inverse goes from S to T. And it's a function such that if you compose it with f, you get the identity. So we want f inverse composed with f to be a function from T to T, which is the identity. Which we sometimes write ID sub T. And ID sub T of any x is just equal to x. It's a do-nothing function. Maps everything to itself. So if f is going to take 5 to A, and when we compose with the f inverse, we want something that brings you back to 5, then f inverse of A had better be equal to 5. And similarly, F inverse of W should equal 4, and F inverse of T should equal 10. And now F inverse, it maps from S to T. And if we start with any number in T, let's say we start with 4, if we apply F to it, we get W. If we apply F inverse, we get back to 4. And that works for all the elements in T. That makes it an identity. And while we're here, we have another identity function. If we take F inverse and we follow that by F, that should be the identity on S. So we can start with any element of S. Let's start with T. If we apply F inverse, that gets us to 10. And then if we apply F of 10, that brings us back to T. And that works for all the elements of S. So that's an inverse on S, or an identity on S. So this would be a definition of the inverse. Does that help? Cool. All right, other questions? No PA1 questions? Every question is fair game. All right, cool. I've seen some completed submissions already, which was awesome. So I'm excited. All right, let's do a quick rundown / refresher on matrices. And I'm not going to hold you to a lot of details on matrices in here, but usually we encounter these in 120, but not always. And when you do linear algebra, Math 215, you'll do lots of matrices. But they sort of belong also in discrete structures, and they'll pop up in some computer science topics. So I want to just touch base on them. So matrix is basically a rectangular array. And for us, we're going to do arrays of numbers. But a matrix is a more general concept. You can have a matrix of functions. You can have a matrix of sets. You can have a matrix of whatever space you're working over. But for us, it's going to be typically something like this. So this is a 2 by 2 matrix. And I'm using integers because I'm lazy, but they're usually real numbers. And so these are columns, and these are rows. And that's really important terminology because we're going to talk about columns and rows throughout this. And so if this is row I and column J, all right, so in this case it's the second row and the second column. We can think of this as the I, comma, jth element. So we can write a matrix as a set of elements like this. So where A subscript ij equals the element in row I and column J. And there's a potential ambiguity there. We could use aij to be the ith column and the jth row. Okay, but we're sticking to this convention. So the first index is how far you go down. The second index is how far you go across. Okay, so this is A1, 0, down 1 across 0. This is across, this is down 0 and across 1, right? And we start our index from 0 because it's a CS course. So that's one way we can represent these matrices. And they don't have to be square. So there's a 2 by 3 matrix. Right, so this first number is number of rows, and this is number of columns. So that's just setting out the playing field here. Definitions and terminology. Well, if you have a collection of matrices, there's 2 matrices, we can define addition, and addition is just done element by element. So this is equal to 1 plus 0, 4 plus 1, 2 plus 1, 3 plus 8, which is just the matrix 1, 5, 3, 11. And we can define subtraction the same way. Bless you. And we can do, so this is addition. And we can do scalar multiplication. So a scalar is basically not a matrix. It's just a number. So for example, if I want to take the number 4 and multiply this matrix by it, it's the same thing as adding this matrix to itself 4 times, which is just multiplying each element by 4. So it gives us this matrix. Multiplication of a matrix by a matrix, on the other hand, is trickier. So to do multiplication, we have to do what's called a bunch of dot products or vector products. So I'm not going to bother defining that, though. We'll just do it. So to multiply these 2 matrices, we're going to get a new matrix. And this first element up here we're going to get by taking this first row and this first column. So first row of the first matrix, first column of the second matrix, and doing what's called a dot product. So 2, 3, dotted with 2, 1. And dot product just means multiply the first elements, multiply the second elements, add them together. So 2 times 2 plus 3 times 1. So that's the 2 and the 2, that's the 3 and the 1. 4 plus 3 equals 7. That's your first element. Now, if you want the element over here in the first row, second column, you take the first row of this matrix and the second column of this matrix, and you dot them. And that's going to be 2, 3, dotted with 1, 6. 2 times 1 is 2. 3 times 6 is 18. That's going to be the number 20. If you want this element down here, that's the second row, first column. Take the dot product of the second row here and the first column here. So 1, 5 dotted with 2, 1 is 1 times 2 is 2. 5 times 1 is 5. That's just a 7. And lower right element here, second row, second column. Take the second row here and the second column here and dot those together. So 1, 5 dotted with 1, 6 equals 5 plus 6 equals 11. So this multiplication of matrices gives you the matrix 7, 20, 7, 11. Have you seen this before? Okay. So there is a way to multiply matrices. And in general, the element in our product in row I, column J, can be written as a sum. I'm going to get this wrong the first time, but that's okay. So we want the ith row. So let's just do it for these matrices. So it's the sum from I equals 0 to 2. And let's call this xij. And let's call this yij. So the element in row I, column J, says take the elements from row I in our first matrix. So x, and I need a different index here, x I k times y kj, I believe. So if we want this lower left corner, we run k from 0 to 2. We take x 1, 0, x 1, 2, and 1, yeah, up to 1. All right. So you can work out the details of that, but basically it's just a summation, right? So multiply, multiply, and add them together. Yeah?
For the last column,
Mm-hmm.
11, isn't it 31?
Did I get that wrong?
1.
Oh, yeah. Thank you. Good catch. 1 times 1, 5 times 6. Good, perfect. I meant to do that. All right, so we can define multiplication of matrices. And we can do this in a computer program pretty painlessly because it's really just a for loop to calculate each dot product. But that sits inside a for loop to calculate each element in a row. And that sits inside a for loop to do that for each row. So you've actually got 3 nested for loops to do matrix multiplication. So it can be a little intensive. 1,000 by 1,000 matrix is going to be 1,000 cubed. That's 1 billion operations. So a little expensive. So there's computers that were built largely in the 90s to do dedicated processing of things like vectors and matrices, just to try to speed this up. And how many people here have done linear algebra, Math 215? So you know that matrices are like the key to everything in the universe, right? Any system of science that you can think of, you can almost reduce to a problem in linear algebra. Whether it's balancing a financial portfolio or finding an optimal solution to some optimization problem, it always comes down to dealing with matrices and solving equations. All right, so there is a multiplication defined. So in general, if we have an n by m matrix, and we have an m by r matrix, we can multiply those, and we'll get an n by r. But the number of columns in this matrix has to match the number of rows in this matrix, because when we do a dot product, we're taking a row here and a column here. They've got to have the same number of elements. Otherwise, this operation isn't defined. So these don't need to be square matrices to multiply them, but the number of rows here, number of columns here have to match. And then what you end up with is a matrix with the number of rows in the first matrix and the number of columns in the second matrix. Okay. So that's multiplication. Now we also have an identity matrix. And it's a matrix with all zeros and ones going down the diagonal. And it's called an identity because if you multiply any matrix by the identity, you get back the original matrix. And you can sort of see why that is. Because if I take this first row and this first column, and I take their dot product, what am I going to get? I'm just going to get A0, 0. This thing times 1 plus this thing times 0 plus this thing times 0. I'm just going to get A0, 0. And if I take the first row and the second column, I get A0, 1 times 1 plus this times 0 plus this times 0. This is going to be A0, 1. And the same thing is going to happen over here. And if I take the second row and let's say the third column, A02 gets multiplied by 0, A12 gets multiplied by 1, A22 gets multiplied by 0. This is just going to save A12. And you can do this for all the elements, and you'll see that you end up with exactly this matrix that you started with. So that's the identity matrix. And you can multiply by the identity, and it doesn't change your value. Unfortunately, we cannot define division for matrices. There's a way to multiply. There's no such thing as a division. But we can still ask, since we can multiply, if we know that matrix A times matrix B equals matrix product, we can still ask, if we're given this matrix and this matrix, can we figure out what this matrix A should be? Can we find something so that when you multiply by B, you end up with P? And that's kind of what we mean by division, right? We say 5 times this is going to give me 20. What is this? What's the thing that when I multiply by 5 gives me 20? Well, it's 20 divided by 5. So we can't really define division, but we can define inverses. So what we can do is define B inverse and say if B inverse exists, it's a matrix that when we multiply by B, it gives us the identity. And also, if we multiply B inverse by B, we get the identity. So matrix multiplication is not generally commutative. Okay, in particular, right? This is a 1 by 3 matrix. This is a 3 by 1. We should be able to multiply those and get a 1 by 1. The element in the first row, first column, is just going to be the dot product of these. So it's 4 plus 10 plus 18, which is just the matrix 32. But this doesn't even exist, right? Because this is a 3 by 1. Oh no, sorry, it does exist. This is a 3 by 1. This is a 1 by 3. We're going to get a 3 by 3 matrix. So switching the order in which we multiply not only gives us different matrices, it may give us matrices that have completely different dimensions, right? So multiplication is not generally commutative. But for inverses, we can multiply either side by the inverse, and we get the identity. And the inverse is just a matrix that when you multiply by b, you get ones down the diagonal and zeros everywhere else. And we can use inverses because if we know that we want A to be a matrix that when we multiply by B we get P, we can multiply both sides of that equation by B inverse, and this becomes A times B inverse is the identity. And A times the identity is just A. And there's a formula for finding what A is. This is a generalization of what we do in grade school, right? When you want to find P divided by B, you take P and you multiply by 1 over B, right? Well, that's all we're doing here effectively. Symbolically, we're taking P, we're multiplying by the inverse of B. That's kind of like P divided by B, but we don't actually write that. And so in 120 and lots of other areas of science, we can solve an equation like this if we can find an inverse for B. And in 120, this comes up in KVL, KCL because you have a simultaneous system of equations, and we want to find the values for the unknowns, the currents or the voltages that satisfy all these equations. We may as well go the distance here. So say you've got 3 equations and 3 unknowns. We can write this as a matrix equation. Because if we do this matrix multiplication, this is 3 by 3, this is 3 by 1, we're going to get a 3 by 1 matrix. The first element's going to be the dot product of this with this, which is just 5x plus 3y plus z. And the second element's going to be the dot product of the second row with the first column, which is 3x plus negative 1y plus 2z. And the third row element's going to be third row, first column, x plus y plus negative 1z. And this is all equal to 10, 4, negative 6. And 2 matrices are equal if their elements are the same. So the only way this is equal to this is if 5x plus 3y plus z is equal to 10, and 3x minus y plus 2z is equal to 4, and x plus y minus z is equal to minus 6. So the only way this equation is true is if those simultaneous equations are true, and vice versa. And this is a solvable problem. If we call this matrix B, we're saying B times the matrix X, Y, Z equals 10, 4, negative 6. If we can find an inverse for B, B inverse times B times X, Y, Z is equal to B inverse times 10, 4 minus 6. And B inverse times B is just the identity, and the identity times X, Y, Z doesn't change it. And so our matrix X, Y, Z will be just B inverse multiplied by 10, 4 minus 6. So you write down a matrix of your coefficients, you find the inverse, you multiply by a matrix of your right-hand sides, and you get a 3 by 1 matrix. The first element's X, second is Y, third is Z, and there's your solution. This is the tricky part, finding the inverse of B. There's algorithms we can use for finding inverses. In general, they're really, really expensive computationally. Enough that if you tried to invert a million by million matrix, forget it. Right, running on a regular PC, it's crazy. But if you can solve this problem of inverting a matrix, you can do finance, you can do business, you can do science, you can do even KVL, KCL. You know, all kinds of things.
So if this multiplication isn't, you can't swap the numbers, right?
Right, it's not commutative.
If B inverse is defined as always going first?
The inverse you can swap.
Okay.
So B times B inverse will be the same as B inverse times B, which will be the same as the identity.
And in the second half of the equation that you just written, right? Is it also the same case that you can swap them and still be first?
No, this multiplication doesn't commute in general.
Okay. So we'll always come first?
Yeah. If we've done it like this, right, which we have.
Oh, yes.
Right? B inverse is going to be 3 by 3, and we're multiplying by a 3 by 1. Right? If we try to switch them around, we'd be taking a 3 by 1, trying to multiply by a 3 by 3. That's not defined, right? Because this number and this number aren't the same. So being able to invert matrices is a good thing. And it's actually one of the benchmarks that's used sometimes when you're measuring the speed or performance of computers. Basically things that relate to inverting matrices. So how do we know we can switch around B and B inverse? B times B inverse is equal to the identity. I can multiply on the right both sides by B. And I can multiply the identity times B is equal to B. And now I can multiply on the left by B inverse. And B times B inverse is the identity. Yep, not an easy way to do it. Never mind.
So it is general for matrices, is it usually left to right, like normal order of operations?
Yeah. Matrix multiplication should be associative. So, actually, I'm not even sure about that. Forget that. All right, I'm not going to go there. So transposes. So a transpose is just the same matrix with rows and columns swapped. So first row was 2, 3. If we transpose it, the first column is going to be 2, 3. Second row is 4, 5. Second column becomes 4, 5. So just reflect around the diagonal. And in some cases, a matrix is the same as its transpose. And in that case, we say A is symmetric. So what's an example of a symmetric matrix? Yeah, 2, 1, 1, 2 would be a nicer example. There's a 3 by 3. So if I swap the rows and columns, I get exactly the same matrix back. All right, so any questions about matrices?
Does the order matter between, like, the one you just wrote, right? Could you have said 3, 2, 5, 4? Would it have changed everything?
Which one?
The top matrix.
This one?
Yeah. You've swapped the numbers inside the matrix. Does that change the value?
Yeah, it does. Like this? Yeah, different matrix. So I should have said this in the beginning. Two matrices are equal means that each element agrees, right? And the position is critical. All right, so that's partially a refresher, partially things you'll see again or are currently seeing if you're in 215. But it's a piece of discrete structures. All right, so starting tomorrow, we're going to switch gears again. We're going to start talking about mathematical induction. And I'll leave you with a sort of motivational example for induction. Suppose you want to walk across the country. You want to walk from here to the Atlantic Ocean. How many people have been to the Atlantic? Oh, you gotta go to the Atlantic. It's a cool ocean. You can actually swim in it, like in September. So you want to walk from here to the Atlantic. And how do you do that? Well, here's the question. Can you take one step to the east? Assume there's like just an open terrain, there's no hills, there's no obstacles or walls or something. Can you take one step towards the east, right? Just lift up one of your feet, put it down in front of you, right? If you can take one step to the east, I can prove that you can take 2 steps to the east. Because first I'll say, okay, take a step, and then I'll say, take another step. Bingo, you've done 2 steps. Can I repeat this and get you to take 1,000 steps? Absolutely. Right? And you've told me that you can always take 1 step. So you can't say, I can't take another step, right? You always can. So if I give you this instruction 1,000,000 times, right, you'll take 1,000,000 steps. Now suppose you want to climb a ladder, which goes from here to the moon, right? Can you go up 1 rung of a ladder? Yes, you put your hand up, you put your other foot up, and you pull, and you've gone up 1 rung. But suppose this ladder is sitting on the space station, your algorithm for getting to the moon is not going to work because you can't get to the first rung of the ladder. So this idea that we can prove you can eventually climb this ladder to the moon requires two things. It requires that wherever you are on the ladder, you can always go up one more step. But it also requires that you can get to the first step of the ladder. If you can't get to the first rung, you can't get to the moon. Or if there's some point where you get to the 500th rung and you can't get one more rung, you can't get to the moon. But if you can get to the first rung on the ladder, and you know that for any rung you're on, you can go up one more rung, you can eventually get to any position on that ladder. Okay, that's basically all we're going to be doing for the next week, is just starting from a first rung and progressing one rung at a time. And it'll get us to some really cool places. All right, so we'll start induction tomorrow.